essentially you have this, when you have a hammer, every problem looks like a nail problem. And we've learned to linearize so many things in optimization that it's kind of scary. And the more natural way of modeling many, many real world problems is a nonlinear formulation. And if your mixed integer solver is what you're going to use, by all means use these techniques. But I think in practice, the Primal solvers will become more relevant in the future, specifically with optimization and uncertainty. And their nonlinear just isn't much of an issue, because you can evaluate nonlinear more or less at the same cost of a linear function. And it's about repeated evaluations more than about maintaining linearity at all costs.
Hello and welcome to another episode of the Decision Intelligence Podcast. Along with my co-host Michael Watson, I'm Vijay Mehrotra, and I'm here to welcome our guest, Dr. Tim Varelmann. Tim has a PhD from Aachen University in chemical engineering and is the principal of Bluebird Optimization. He's also very engaged with something near and dear to my heart, which is building out a tool called GAMSPy, and we may get to talk about that a little later. Tim, I'm super interested, given your background in chemical engineering, how you found your way into optimization. Let's start there.
Sure. When I started studying, I actually started twice, because the first time I chose business engineering and that wasn't for me. So after a year, I said, no, this is not it. And I was looking for another course of study, and I found one called computational engineering science. And it was designed from the first semester on to teach us how to professionally build simulations. So I really came from the simulation side, did a bachelor's in it, and then was already quite good in doing simulations. And then over the course of my master degree, optimization started sliding into the picture. And to me, it was presented as, hey, you have this simulation as where you develop a model and you can put some inputs in and then let the computer calculate into the future. And basically, if the computer calculates faster than real time, then you can make predictions about the future, and that's cool and valuable. But for optimization, the way I learned it is you take the same model, but you invert the order in which you calculate, because you start at the outputs. You say, hey, I want the best possible outputs, and let the optimizer figure out the way backward through the model to give you the best inputs that give you the best possible outputs, in a sense, right? And yeah, I thought that was very interesting. It matched with my simulation predisposition, and I ended up doing an entire PhD with algorithm development for the energy transition.
Oh, cool. So we'll continue this line of questioning and kind of extend your your path here, because now in the last several years you've been talking a lot about combining machine learning with optimization. So what's your kind of take on that, and how have you approached that?
Yeah, the general trend is, I think we have more and more computational power. That's just what's happening. And therefore you can make problems more and more complex. And obviously, once it's possible, one of the natural extensions is to put machine learning models that are in and of themselves quite complex models and integrate them into optimization as just one piece of multiple other things and connect them. And machine learning has some great capabilities to describe things in their models that other ways couldn't do before as elegantly. And therefore, it's, of course, very interesting piece to put in context with other moving parts of optimization models.
Cool. Let me just do one follow-up on that. When you talk about integrating the two, are you talking about just you run machine learning model, get a prediction, and then sort of pass that prediction as an input into the optimization? Or are you passing more than just like the average input? Are you passing like variability that comes out of or variability estimates that come out of the machine learning model? Like when you integrate the two, how do you define that?
What I've seen working is three different ways. And one of them is what you mentioned, essentially optimization and uncertainty, where the uncertainty is powered by machine learning, let's say. Right?
Okay.
And you've had other guests on where I've listened to this podcast talk about this in depth. The second one that I've seen work is when in your optimization you describe something. I mean, I'm a chemical engineer by training, and there are interesting things, but they are typically very nonlinear and just computationally nasty to deal with in optimization. So it is possible sometimes because, for example, a neural network is a universal approximator of whatever you give it. Train a neural network on some complex nonlinear thermodynamics of mixture, let's say. you will always have the same sigmoid function in that neural network. You can overall, by good training, make sure that the neural network describes the thermodynamic within an acceptable approximation error range. And then you use the neural network inside of your optimization instead of more nasty nonlinear equations for thermodynamics. And then that speeds up the runtime essentially of the optimization because you have structure that you can exploit. Right. And the third way of combining machine learning and optimization, I would say, is what I've done in my freelancing, for example, when you just don't have any physics, right? You only have data and there is nothing else. For example, when people like I have had a project in the past, optimization for websites and website design. How do we do certain decisions on website design or things to show people? We have observations of how people behave, but there is no first principle physics of human psychology or human behavior on websites. So all you have is data, really. And of course, machine learning shines with large amounts of data, and then you can still infer some good knowledge and make good decisions based on that.
I know there's been a lot of evolution in the solver landscape in the last few years. How do improvements in solvers kind of change the way we think about a kind of modeling machine learning inputs? And kind of hand in hand with that, kind of what are some of the tricks that you use to deal with nonlinear and non-convex issues?
Okay, that's a mouthful.
That is
First of all,
there's a
maybe
lot there. You can break them apart.
Yes, let's start with the how to solve developments.
Solver improvements in progress. Yes.
So I think I see two basic things going on. One is the classical dual solvers, such as Gurobi, is one of the companies that is hiring successfully and aggressively at the same time right now. They are traditionally coming from a mixed integer linear programming domain. But since a couple of years have already amped up their nonlinear capabilities as well. And last time in October, when I was at a partner event for Gurobi, they announced, at least like to that people, the partners and people who were there, that they plan to be competitive by the end of next year in terms of nonlinear computation as well. So they are just amping up their general nonlinear capabilities. And of course, if you have nonlinear functions in machine learning models from sigmoid functions, if you have nonlinearities in your decision trees in random forests, stuff like that, if you have a generic solver that is able to work with nonlinear programming, that's better because it just works faster until you have a solution. The other train is this development and the way that primal solvers have become interesting recently, I would say. So they have just a completely different approach in some ways to what optimization is. First of all, they just completely get rid of the idea, hey, we are proving optimality. And primal solvers are just saying, hey, we want to make good guesses. And this goes back to simulation again, because what they do is they simulate things, see if it's feasible, simulate at the end of the simulation, they get sort of an objective value, and then have clever ways of finding the next thing that is the next point that is worth evaluating, which is an entire simulation again. And that works very well with optimization and uncertainty.
What's an example of a primal solver? Do you have is there companies you work with or products you work with?
I've worked with Seeker in the past. I had a client in Silicon Valley where we did exactly that, optimization and uncertainty, and used Seeker for the implementation. Warren Powell has published and put out his work to the world, which is very theoretical. I have his book here. I haven't really read it yet. I mean, not back to back at least, because it's like 1,000 pages and
yes,
super theoretical. And but like the content is good, right? And there's more to it. And I think Seeker is one of the solvers that really implements this simulation optimization approach very well. There's also Hexaly, for example. They also a primal solver who not necessarily care much about proving optimality, but just finding good points, let's say. Those are the options, I think.
So I want to kind of dig in further to just kind of help me and help our audience kind of ground this notion of integration of ML with optimization, because I feel like my perspective is naive. I always think, gosh, inevitably we've got some uncertain components of our of our optimization problem. Most commonly in the applications I've worked on, uncertain demand. And so
Mhm.
we're typically using regression or machine learning of various sorts to forecast that demand. And typically we'll pass in a point estimate or a distribution and tackle it with either traditional optimization or um, some kind of stochastic programming approach. Um, but it sounds like some of the use cases that you're talking about are more interesting than that. And I'd love to have you kind of identify, um, just to describe a couple of situations where the integration between machine learning and optimization is not so simple as simply forecasting demand or something.
Yeah, there's different ways of thinking about this. Like Netflix is a prime example. They've really popularized machine learning, where the difference between prediction and decision isn't really there, I think. Because when you're on Netflix
Right.
and you have, let's say, 3 slots of things you can recommend, right? I have just finished a movie and now they want to keep me on their platform, so they recommend me 3 other things. They have a model, and that model is a machine learning model which outputs probabilities that I will like
Yes.
other movies. And that probability is pretty much a one-to-one mapping to how they should decide, because they should just decide the best probabilities that they get. So order the outputs by probability, and the first 3 is exactly what they are showing me, right?
Right. I mean, and
However,
that's
if
a
you are
case where, when I think about that kind of problem, to me, that's a case where, in fact, as you said, the probabilities, the output from machine learning, 100% drives the decision, or
exactly,
98% drives the decision. Um, but I feel like the the cases that are more interesting is where the decision complexity isn't obvious from the
exactly.
propensities or the predictions.
Yeah, that's exactly what you're saying. There is there's not always, but in general, there is a difference between making decisions and making predictions. And like one of the applications I've worked in a lot is electricity grids. And there, the prime thing to forecast is the weather. Okay. And then you have a couple of downstream effects. From the weather, you can infer how much. So you have, first of all, a solar forecast, and then you have maybe a wind forecast. And then you have how much wind power do we get from this as a distribution that is
Yes.
pretty one-to-one influenced by the wind forecast. And you have the same thing for photovoltaic. But then you're on the electricity grid, and that's an entire, like, very sophisticated model of technical things moving that I even don't understand, right? Because I'm not an electrical engineer, but I work from the systems perspective. And lots of things are happening in the electricity grid. And if you have a forecast that says how much renewable energy you can generate, that doesn't have a direct influence on the decisions you're making, how to operate an electricity grid, which transformation to use at which point, which lines to use to route the energy through, where you need a fossil fuel-based power plant to keep the stability of the grid up and stuff like that. So those are completely different decisions. They are influenced by your forecast, but there is an entire amount of physics model that is very complicated in between the actual prediction and the decision you want to make.
Yeah, so I want to change the topic a little bit, but it might relate to what we've talked about. Sort of a different kind of question is, I think you write also about maintainable optimization code. How do you think about that? Like, the problems that you've talked about up to now sound fairly complicated. How do you write those in such a way that you, the client, can maintain this code over time?
Mhm. So this is an idea I've taken from plain vanilla software engineering, essentially. Since the 80s, there has been literature and principles of good software engineering, and essentially it boils down to when some software is easy to maintain, that means it's easy to change. I mean, that's essentially why it's called software, not hardware, historically, right?
Okay, yep.
But software just changes all the time, and if it's easy to change a software, then it's easy to maintain it. And of course, like not changing anything at all is not a change. So 0 is a lower bound for that, if you want, in an optimization speak. And therefore, the best thing you could achieve is just one change to, whenever your requirements for the software change, you just need to make one change to your software. That's the ideal. And how do you achieve that in optimization? I think algebraic modeling works pretty well with this. Um, it's a pity that it's called algebraic modeling for historical reasons. I like to call it set-based modeling because it's more visceral and easier to grasp what's going on.
Right.
Because you can say, hey, I have a set of power plants, I have a set of photovoltaic plants, stuff like that. And I just iterate over this set. And every time I have a power plant, I make some decisions, and I have a decision variable that also iterates or like expands over the set of plants as a domain. And then in your software, what you need to do is just write one line of code. Here I'm declaring a variable for the power plant, and that expands over that entire domain. And now you have a different grid. All you need to do is update the set of power plants, but you don't need to change that line of code where you define, hey, I have a variable for each of the power plants, because this for each notion is how you make the code maintainable. That's an easy way of thinking about it.
That's awesome. We try to stress that too, in the academic sense when I teach this stuff is like get the students to separate the model from the data. And then, because I think what you've described is just a great way to define the model in some completely generic way so that you can now feed in 10 plants, 5 plants. These 8 plants all have the same rule apply to them. I don't have to have a rule for each plant.
Yeah, and it also helps you in testing tremendously, right? Because you can test for a use case where you can really, as a human, calculate on pen and paper with like just 2 elements in your set, find the optimal solution, and you have your test case, and then you have exactly the same code because you don't need to change it. You only change the data for your large scale things. And
yeah. Does it get harder? The algebraic notation, set notation. Is it get harder as you start combining machine learning models? Like you talked about embedding a neural net into a problem. Does it get harder? Are there new challenges there? Or is it still just the same challenges to keep it as separate as possible and as easy to maintain as possible? Or is there something new there?
I think in principle, it's the same problem as with other things. Obviously, like there's a new level of abstraction coming in, for example, with the layers of a neural network. But there are tools that support that. GAMSPy is one of them that does a tremendous job, in my opinion. And like the integration of optimization and machine learning in GAMSPy is really one of the unique selling points of GAMSPy, in my opinion. But yeah, once you have these abstractions in place and you have a library, if it's GAMSPy or another one, that you can just say, hey, I want a neural network, and it has as many layers, and each layer has so and so many activation functions or like neurons, then you're good to go, essentially.
Relatively quickly as well, because of the library.
Exactly. Yeah. I mean, the library does the heavy lifting, or it has done it upfront. Yeah.
What's the downside of that approach? Is the down, like if you have exactly the mixed integer program, it's like you've got sort of proven optimality. You got a sense whether it's going to solve or not. Is there a downside to combining too much of that in one of these models, that you just have to be more careful with the solves? Small changes to the data, not necessarily making the data larger, can lead to it not working, not running in fast enough, or the solutions not being high quality. Is there stuff people need to look out for? Like
I mean, a lot of the things you mentioned are just general problems of nonlinear problems, and machine learning tends to become nonlinear pretty quickly unless you really make a point of, you could use ReLU activation functions in a neural network, for example. You can model a ReLU activation function with mixed integer modeling techniques, and then you can remain linear. But if you don't pay specific attention, then you will likely have a nonlinear problem. And then all the things you mentioned, they are just basic issues that always come with nonlinear problems. Also, nonlinear optimization just has more trouble with scaling, right? You can scale mixed integer linear problems pretty easily, but if you do the same amount of scaling to a bigger size to a nonlinear problem, you would run into problems earlier with until the runtime explodes in practice.
What's your advice on that? Like here's my standard advice, and critique me and tell me where I'm wrong. I kind of think when we teach this and when people start out, they should start out with simple and stick with mixed integer program and work really hard to avoid nonlinear. Like I think we should stress, like, please try to do it as a linear or mixed integer program first. And then once you really have that, then expand to nonlinear. That's sort of the approach I have. But do you have any critiques of that, or should I not give that such black and white kind of advice?
I think it certainly used to be very good advice until 2 or 3 years ago, I would say.
Yeah.
Like with these Primal solvers, I personally had to unlearn a lot. And it was easy because when I did simulations earlier on, it was pretty natural that you can write down nonlinear things. But in optimization, and I've done a lot of optimization and really also learned how to do many things. And essentially, you have this, when you have a hammer, every problem looks like a nail problem. And we've learned to linearize so many things in optimization that it's kind of scary. And the more natural way of modeling many, many real world problems is a nonlinear formulation. And if your mixed integer solver is what you're going to use, by all means, use these techniques. But I think in practice, the Primal solvers will become more relevant in the future, specifically with optimization and uncertainty. And their nonlinear just isn't much of an issue, because you can evaluate nonlinear more or less at the same cost of a linear function. And it's about repeated evaluations more than about maintaining linearity at all cost, right? Because also it's like what you mentioned is the penalty for the very first nonlinear thing is super, super high. And as soon as you have the first nonlinearity, the rest is basically for free, more or less, right? Unless the first one was maybe quadratic and then the others are more nasty. But yeah.
All right, you gave me some work now, Tim, so I got to unlearn some things. Thanks.
I mean, I think we all do, right? As our compute power grows and as our tools become more and more sophisticated, we've got kind of mental constraints that we're used to operating under that we've got to kind of let go of and unlearn. And that's a good story because our possibilities are growing and the kinds of things we can solve more effectively are increasing. But there's definitely habits to shake.
Absolutely. Yeah. I mean, everything that AI does is impacting this, right?
Oh, God.
Whenever there's a new development, some things you have to relearn and unlearn. And unlearning is the hard part, I guess.
Yeah.
Well, so Tim, I'd love to have you talk a little bit about a case study around inventory optimization at Drift. Can you tell us first kind of who is Drift and what do they do?
Sure, yes. So I was alluding to this earlier. Drift is a Silicon Valley-based startup. They write agents for industrial clients, AI agents, and they are not the first ones who approached me to actually put optimization under the hood of their AI agents. For Drift, the case was Drift had an end client that wanted to improve the way they do the storage optimization, essentially, right?
Yes.
So the question really was, when do we restock? And if we make the decision to restock, how much do we restock? And essentially, in the terms of inside of Zika as a solver, which we used, these are just two optimization variables. You want a threshold for inventory that remains, and if you are above that threshold, then everything's fine. You don't need to restock. But as soon as you go under that threshold, then you will trigger the reorder. And then the question becomes, how much do we reorder? Because these things are like, if you have thousands and maybe even millions of SKUs, you don't want to maintain that manually and have a person who's like responsible for updating these things every week or even every month. That's just totally unfeasible. You can do the math if you have a million parts, how many people you would only need to pay for just updating like some parameters. So you really want this to be automated. In the past, this hasn't happened. And yeah, you have a lot of data, right? And this comes back to your question on demand uncertain. This is exactly what was going on here. So Zika is very interesting because it provides you with a bunch of just library features for distributions, but you can also extend it and customize it. And that's what I did for this particular project, where the demand that we've observed for a particular part in the past informed the way we sampled the demand for the optimization under uncertainty. And we didn't really have to come up with any categories. That's initially what we started with. We wanted to say, hey, maybe we have parts that are pretty stable in demand and just always have the same demand, and you just have a simple, relatively low threshold for when you reorder, and you don't need to reorder as much because it's very predictable. And then you have other parts where you have lots and lots of demand at once, and then for half a year, nothing or so. And while we started with this categorization, we pretty quickly learned it doesn't give us much, because whether this period between demand spikes is half a year or 3 weeks makes a big difference. And it's very important to just do this on a SKU per SKU basis, really. And we had the data available, so we used them. I've customized sort of a custom distribution. So for each part, you could automatically generate this custom distribution, how the demand looks for this thing. And then essentially just let's say 100 years run and say, hey, over the course of 100 years, this would happen, because for 100 years, you just do a forward simulation with any given parameter.
Right.
Where you say, hey, I'm just testing this threshold for my inventory for reorder point and another threshold for the lot size. And you just simulate it through and see what the end result is. And then you do that for 100 years, and then you try again for another parameterization. And what's really interesting about this primal solving, also something I had to unlearn, is you can like a priori say, hey, I want this part to compute for 10 seconds. Or this is an easy part for some metric, I know that, and 1 second will suffice. And so before you start the computation, you know when you will have the result. That is different in mixed integer optimization, and it has very exciting implications for just practical use.
Is the core of it really? It's really like it's basically a discrete event simulation, some type of simulation that's running in the background. Like is it? Can you get statistics on the discrete event simulation like you do out of that, or is it?
Yep.
Okay.
Zika supports this out of the box already. Like what exactly you do inside of the simulation is also highly customizable. If you have the C++ knowledge, but I have it, and so you can program some custom function to say, hey, anything fancy that's going on, you could put into the simulation. And I mean, the team at Drift is also very eager to try out new things, and they have many ideas. So we tried lots of things, and therefore, having this super highly customizable simulation model. And then just executing it lots and lots of times. And then the secret sauce of the solver, in this case Zika, is how do you pick the next simulation to evaluate? Because they know they only have 10 seconds, for example. And early on, they will just, right, you outsource the exploitation trade-off to the solver. Early on, it will just explore widely. And then once it knows, hey, I only have 1 second left, I really need to exploit the best points I have found and just look in the vicinity. If I can find something better close to it, it will do that for you.
Cool, because in the past we would have just like it would have been that part would have been manual. If I had a simulation tool available to me, I would have had to come up with some rule that says, all right, try 10 and 50, try 10 and 60, try 11 and 12, and then now,
and then you have essentially a for loop that always calls it again, right? And Zika can also do this more effectively internally, because they will have like a computational graph, and if some parameter hasn't changed or some intermediate result hasn't changed, it won't re-evaluate the things that come after it. So your simulation is evaluated very effectively also.
Oh, cool. Did you compare the results of that with just like some closed form inventory equations to see how it would compare?
Yes. I mean, these are like a mess, and just I couldn't recommend it at all, because all of these formulas, what do? It's just normal distributions all over the place. And the world is not normally distributed, like not at all. So you have analytical formulas, and it's just a complete mess. So I mean, we ended up implementing this Zika-based SKU optimization and ending up saving the company millions and millions of euros.
All right, the longer we talk, Tim, the more I have to change everything that I say. So you're giving me lots of work here.
Oh,
all right, Vijay.
Well, it's pretty interesting that application is not just an application of simulation optimization, but a super interesting application of agents, right? Given that you've got this massive SKUs to track, and as you said at the outset, there's no human, and it's not a human scale problem. There's no way we can do that. But agents are tireless, and they can keep executing. And am I seeing that the right way, Tim? That sort of the algorithmic intelligence combined with the agent execution is where the value came?
Yes, 100% spot on. Like it's really nice to know in advance. I will let this run for 10 seconds, and then whatever parameters I have tried, the best one will win, and that's what I will take. You have to, like in this case, it was pretty easy to ensure feasibility. So not many guardrails and needed to be enforced for that. Because if you have a bad set of parameters, you just have either a high stock out ratio, or you have high cost for keeping everything on stock that you don't really need. But it's typically feasible. In more complicated cases, the feasibility may be a bit of an issue that you may have to spend more time on. Because if you computer for 10 seconds and the optimizer in the end comes back, hey, I did everything I could for 10 seconds, but I couldn't find a feasible solution, then you're in trouble in this setup. But exploiting this knowledge that, hey, I know this will run for 10 seconds, that's really good.
So kind of coming back to that, the engineering of the whole solution. So it sounds like one part of the problem was just where you optimize and figure out what the order threshold was, and then the order up to point. You sort of figured out those two parameters. Was there other engineering where you had to, you wanted to update the demand? As demand came in, you updated that and sort of reran to get the new parameters. Was there other things on top of that where you were predicting stockouts or predicting issues like ahead of time? Like this is where our inventory targets, but for whatever reason, demand has picked up. Please watch out for this part because it's going to run out of inventory. It's going to stock out sooner than you thought. Was there other things like that part of the overall solution?
Yes, like you can pretty simply adjust this custom demand. For example, if you know, hey, the demand is going to be 20% larger than in the past, you just add a factor of 1.2 and let it run with that. That's possible pretty easily. From the engineering point, because of the flexibility, not so many difficulties were there. What was more difficult really was translating this back into business language, right? In this case, it was pretty nice to use like a Pareto front because we had essentially the storage cost and the stockout risk on the other axis. So multi-objective optimization in the sense, but only 2 dimensions. That's good because then you can have it on a nice Pareto front and right, and visualize to business people who are not who don't have a technical background and say, hey, this is like a kink in the distribution. It starts pretty flat, so it doesn't really matter. And if you have like high cost, you will essentially have no stockouts. But then you will start to have a kink, and now it's for you to make a strategic decision. Do you want 10% stockout risk, or do you want 5%, or maybe do you want it differently for different parts? Because where this kink starts is at different points and stuff like that. And that works really effectively. But it took some iterations to work this out. And yeah, I mean, first of all, it's just showing the people this kind of graph and sort of gently customizing them to this. And then as we go through the iterations, hey, you've seen this before and you know how this worked and you've had this insight in the past, remember that. And yeah, so that was more of a challenge really.
So I got a couple of questions as we wrap up. I think I'd love to get your sense of what's most exciting to you about the advances we're making in essentially using machine learning to deal with uncertainty in conjunction with optimization. Where do you think things are going? What's most interesting to you about?
Yeah, I mean, we have this Warren Powell framework now. And as I mentioned, this is super theoretical, but I think there is really something to it. And I'm very curious to see how this will pan out once it gets implemented more and more. So this whole entire approach of doing policy-based optimization, it's also super, super practical already, right? Because people in the past, what do they do when they didn't have this advanced analytics? They used some form of policy, as Warren Powell also points out multiple times. And what you can do now is say, hey, I can do this, I can scale this up. If I have 1 million SKUs, I can do like precise optimization for each and every individual part. And also, I can tune every parameter of your policy. I don't just have to say, hey, I will have a safety stock of, let's say, 50 units. I can say for this particular unit, it's like 73, or maybe just 42. And yeah, that just will release a lot of economic value, in my opinion, when we will be able to scale this up. And I'm very curious how this will pan out.
So on that note, kind of hand in hand with that, to me, I'm wondering, where do you think the sort of the challenges are there in terms of the biggest skill gaps, whether it's modeling or solvers or decision framing or communication? Because Warren's framework is very rich, but it's so much more structured than most organizations I see, and their ability to kind of think.
There are lots of moving parts. I mean, I think that's spot on. Lots of moving parts, and I wouldn't really make a prediction which of the ones you mentioned will be the showstopper, like the bottleneck at least. It's true. There are lots and lots of moving parts. I don't see also that any one of them right now will be like a major showstopper. So everything in isolation seems we should be able to work around the problems that come with larger scale and just applying this more broadly. So yeah, that's like what the future will tell us.
Well, yeah, I teed you up with that question because Mike knows what my bias is. My feeling is that the technology is always going to be ahead of the human decision makers and their ability to structure and digest things. Uh, but uh, but what I've taken away from our conversation today is that there's quite a lot of complexity to the mathematics and the data flow around combining machine learning and uncertainty with optimization, in addition to the human issues. Mike, can I throw it over to you for a last question?
Yeah, let's just wrap it up, Tim. It'd be easy. Like, where can people learn more about you and the work that you're doing?
Sure. I mean, I'm active on LinkedIn. You can follow me there. I also have a resource prepared for your listeners, which you could put in the show notes, I guess.
Yes.
We'll do that.
On how to combine machine learning and optimization practically. So check that out. It will send you to my newsletter, which goes out every 2 weeks. And where I just share from my practice as an independent expert in optimization, what I come across in my day-to-day life. Then I have a website. It's called Bluebird Optimization with a little blog that is really just a random collection of stuff from Harry Potter to really serious energy transition things. So those are the things I would point people to.
All right, perfect. Thanks for the conversation today, Tim. It's been great. I learned a lot.
Yeah,
Awesome,
it's been
thanks.
really wonderful to kind of get the perspective that you have, given the depth of focus you have in this area. I think our listeners are going to take a lot away from that. Thank you. And for those listening today, thank you for joining us. If you haven't subscribed yet, you can subscribe at Decision Intelligence Podcast on Substack. If you like the show, tell your friends. If you didn't like the show, tell your enemies. And we'll see you next time.